All right, so for our second lesson here, our second real lesson here in Unit 2, Part 2, we're going to solve equations again by factoring. We're going to remind ourselves of that. How do we accomplish those tasks? But then also, we are going to try to solve by taking square roots. So this is work that you would have done back in Algebra 1, and it's been a little bit since we have attempted to do these kinds of things. And so since it's been a while, it is helpful to have some review. So again, we found the zeros to a quadratic function. All right, the zeros again are the x-intercepts, these values of x that make the output y equals 0. And we explored how to do that with factoring in our last unit. We went ahead, or last half unit, went ahead and said that this factored form gave us this equation, and we could solve that equation by taking each of the factors equals 0 and solving separately using the zero product property. And so just in review, when we are factoring, the first thing that we need to do is make sure that we're in standard form. The second thing, find a GCF if there is any greatest common factor. And then we factor, and then here, this is kind of our dilemma right now, because we practiced at length how to do guess and check, thinking about how these expressions will multiply, and then using that kind of in reverse to make smart guesses. To see how these expressions would factor, or we could do the directions that I had in your video where we would use the A-C method, factors of A times C that add up to B, then do factor by grouping, etc. But at the end, once we have our factored form equals 0, we can use and apply the zero product property. So here again are just a few reminders of how you might approach this work. Here are some additional examples. We see that there's a greatest common factor of 3, so that we can try to, again, picture how we could factor out these expressions. And then, of course, we want to be able to do some guessing just to make sure that we can, just make kind of smart choices about how we will multiply these. So this is actually going to be a +2 and a -1. When I multiply those, I'm going to get 3x squared. I'm going to get 6x minus 1x is going to give us our 5x's and then -2. So if I'm going to solve this equation, obviously this factor is never going to equal 0. So if I set 3 equals 0, it's not going to work. There's no solution on that. But when I take 3x minus 1 equals 0, I'll get 3x equals 1 and x is equal to 1/3 as one of my answers. And then I also have the other factor equals 0 to find out that x is equal to -2. So I got 2 zeros. That means that there's an x-intercept at -2, 0, and x-intercept at 1/3, 0, and so we found 2 of the solutions. You can go ahead and try these ones. Over here, we have a situation where once we get this into standard form, we just have an A term and a B term and there's no C term. But we do have a GCF. If I factor out a 3x from here, I'm left with x. If I factor out a 3x from there, I'm left with 2. And so this is completely factored. It's not factored through the guess and check. We just have a GCF. This actually works out pretty magically. This factor equals 0 when x equals 0. And this factor equals 0 when x is equal to 2. So we have our 2 solutions. If we were to graph these functions, and this is just kind of a rough sketch, but we would see that this would have a 0 at -2, 0, and over here at 1/3, 0. Over here, this picture is kind of a strange one. This one's going to go through the origin. All right, it's going to go through the origin, and it's not perfect, but this is generally what we're going to have. We're going to have 0, 0. And then we're going to have 2, 0. So we can predict what those graphs are going to look like without having to graph it. And we can find those zeros, again, by factoring. Go ahead and do B and D as you have need. Obviously we're expecting that we know how to factor, and so we want to do a quality job with that. And then again, here are a couple others. 4x squared minus 20x plus 25 equals 0. Here I don't have a GCF, and so we have to figure out what are 2 things that multiply to give me 4x's if I'm guessing and checking. We're going to do 2x and 2x and see if this pans out. And it looks like what we'll have here is a -5 and a -5, so we actually have 2x minus 5 squared equals 0. When I FOIL that out, I get, or double distribution, I get 4x squared minus 10x, good, and then plus 25. Again, guessing and checking is really the way to go, but if you want to do full AC method, we can get some more examples with that. But this factor will equal 0, and the other factor will equal 0. We don't have to do this twice. I'm showing you it twice because I'm going to get the same answer 2 times. All right, and we're going to talk about this as a strange situation. This is called multiplicity, because I have multiple zeros at x equals 2.5 or at x equals 5 halves. All right, you go ahead and try to factor that one. But this again is to review. All of that I just did was stuff that we've already done before and that we should feel very confident with. And so I apologize for spending 5 minutes of your time doing things that we've already done. But I know that there's a handful of folks, roughly, I mean, there's like probably about 20% of us that need some help on factoring from Algebra 1 and from last unit. So I want to make sure that you've got that under control for this situation. So the reason why I wanted to introduce that was, again, just to remind us that factoring is a method for solving quadratic equations, but we will have some trouble with situations that are not factorable, right? If we can't factor the expression, then we can't find the zeros unless we learn some alternative methods. So one is when we have irrational solutions, right? Where this isn't quite, a rational number, we're not going to find that answer by factoring. Or if we have non-real solutions, we've talked about imaginary numbers, and there are quadratics that don't have an x-intercept. So where are the solutions to those corresponding equations? If there's no zeros, then how do we understand that? If we can't understand it graphically, if we can't represent this solution, then we want to make sure that we are finding out exactly what those real, I'm sorry, not real, but what those solutions are, what numbers will make our equation true. All right, so we might have a situation where we have two irrational answers, and what are we supposed to do with that? So again, when we have a quadratic, there's a couple things that you need to understand. The first is that if it's an x squared equation, then that means that there's two solutions. We saw that on a lot of the work that we did, except for the ones where there was multiple zeros at the same spot. So if the vertex is on the axis, that means there's two zeros but in the same spot. All right, so we'll just say that there's one real solution even though it happens twice. A complex or imaginary situation, if there are complex solutions, that means that the parabola does not touch the x-axis. So there's not a real zero there, there's just an imaginary zero. And there's probably a pair of them, right? And we're going to find out what those are. But most cases we're dealing with two real solutions. They might be rational numbers, they might be irrational numbers. We know how to find the solutions when there's real rational answers. But what do we do when they're irrational or when they're imaginary? Well, here is one other approach that we can take. Again, what we want to make sure that we have is our equation in standard form. When it's in standard form, if we have a solution where b equals 0, that will apply to our work today. If we don't have b equals 0, then hopefully we can try factoring. If factoring doesn't work and b doesn't equal 0, then we're not going to be able to do much with that yet. We'll have to stay tuned for 2 more lessons. But basically we're just going to do algebra, all right? They sometimes just call taking square roots doing algebra because you're just performing inverse operations to solve these equations. Let me show you a little bit about what I mean, and I'll do probably most of these over here. But here we have this situation. Now these are not in standard form. I'm actually not going to put that in standard form, but I am going to do a little bit of computational work here. We want to make sure that when we are working with this situation, if we do the inverse operations to solve for x, I'm going to divide both sides by 5, and then I'm going to take the square root on both sides. Now, before I take that square root, I want to remind us of a couple key situations. When we are taking square roots, we want to make sure that we are attentive to a couple key facts and features. And this one might be the easiest one to kind of see that with. All right, we get negative 48, I divide both sides by 3. And what I want us to maybe understand, which is, again, maybe just a difficult thing to request of folks, but when we are doing this work, and let's look at example B in particular, this is going to be a good one for us to check. When I divide both sides by 5, I get 36. All right, I wanted to find one that actually kind of worked out a little bit easier for our brains, right? So the first thing I want to mention here is we added 180, we divided by 5, okay, great. So now I have this equation, x squared equals 36. And just a couple class meetings ago, when we were simplifying square roots, we would say, oh, the square root of 36 is 6. But if I'm taking a situation where x squared equals 36, there's two answers there. There's two numbers that when I square them, I get 36. Write them down if you think you know what they are. So what we should notice is that there should be a positive and a negative square root. That we should get a positive 6 and a negative 6. So those are both solutions. You can write it like that, or you can write x equals negative 6 x equals positive 6. You can write it two different ways, totally fine with me. But when we're taking square roots to solve, we have to consider that there's a principal or positive root and a negative root. A negative number that times itself will also equal this positive amount. Now that gets a little bit dicey when we're dealing with imaginary numbers or irrational numbers, because it might be harder for our brains to understand how this is going to be the same process as that. When I'm taking the plus and minus, the positive and negative square root of 30, when I'm taking the positive and negative square root of 8, when I'm taking the positive and negative square root of negative 16, we want to make sure that we are doing a quality job of representing first and foremost the positive and negative possibilities there, but also simplifying the square root. Now when it's something basic like this, we know that the square root of negative 16 is 4i, so I get positive 4i and negative 4i. We'll talk about how that solution works probably another time because I don't want this video to be too long. But over here, we should notice that this is 3 times 2 times 5. There's no other factors there, so this is just positive negative I times the square root of 30, which means it has two solutions, I times the square root of 30 and the opposite of I times the square root of 30. Those are two answers because we have a positive and a negative I squared root of 30. Over here, the same deal. We're going to simplify that, the square root of 4 to the square root of 2. And so this is just a real number. It's just irrational, all right? It's still real. There's no I. There's no I. These are imaginary. These are real. This is a whole number. It's rational. We could solve that by factoring if we wanted to, but it's probably faster to do this. And then there's an irrational answer where we would have to use these square roots, and we can't use factoring. So again, I wanted for you to be able to see these situations. These imaginary ones, if I were to graph these wouldn't intersect the x-axis, right? We'd have this situation here. Over here, we would have, we would have that situation with 0, 48 way up here. And so we don't have zeros on these items. We have these imaginary zeros that we find by doing this process of taking square roots. Let's go ahead and do a few more here. You're like, oh my gosh, Mr. Hibbett, too many examples. I've never heard a kid say too many examples. So let's go ahead and give these a shot. Let's see how we do. So again, we've got an A, we've got a constant, we've got a constant. Let's not actually worry about putting that in standard form, but let's go ahead and add 91 to both sides. And then we are going to divide by 2 on both sides. We are not going to do this as a decimal. We're going to leave it as a fraction because we can simplify square roots involving fractions, but we can't simplify square roots involving decimals, right? Very well. So we want to make sure that we do a decent job of taking this expression here and that we take the square root on top and the square root on bottom. And so this gives us, 9 and 11. But then we're going to have to rationalize that denominator. So I'm going to let you finish that, but we're going to multiply by the square root of 2 over the square root of 2. Actually, I won't let you finish it. I'll just do it for you because I'm a nice guy. So x is going to equal 3 times the square root of 22 over 2. All right, and the plus or minus, the opposite and the positive value. Over here on this one, you get to try, and I'll give you the answer when we get together in class. But then for these two, I want to show you that we do not need to, if we're going to be taking square roots to solve this anyway, then we do not want to expand this out only to make our lives a little more difficult. We're doing a lot of work when we could just take the positive negative square root to get rid of that squaring, right? Take the positive negative square root to get rid of that squaring. Right? We want to do a good job with that. We want to make sure that we can simplify this square root before I deal with any of this nastiness. So over here, we know that that's going to be 36 and 2. So I get x plus 2 is equal to plus or minus 6 squared root of 2. Now here's where this becomes maybe a little bit messy and where some of you aren't going to like the format in which we write these answers. But we're going to tough it out, we're going to get through it, and I think that you guys are going to be fine. What we're going to do is subtract 2 from both sides. But when I subtract 2, it's basically the same as adding negative 2. We're going to put that rational part first and the irrational part second. So we're going to write our answer as x is equal to negative 2 plus or minus 6 square roots of 2. I don't need you to understand that quite yet. I just want for you to write it down and think about why we want that to be written this way. Just think about why we want it that way. And I say we because you are going to want your answers like that as well. Over here, we're going to add 3 to both sides, but we're going to put that 3 in front of that square root of negative 49. Now, we know the square root of negative 49 because we did that work last time. That is going to be 7i. All right. Now, again, you could and probably should simplify the radical first before moving that 3 to the other side. But again, think about why we want that 1 in that format instead of plus or minus 7i plus 3. All right, we want them in that format. All right, that should really be the end of things. Really, it was one example, but maybe some different types of situations. But this is solving quadratics by taking square roots. And my hope, my earnest hope for you, is that this Algebra 1 review tied in with this new Algebra 2 content, dealing with these imaginary numbers, is going to be a sincere win for us. Please let me know what questions, if any, you have.